All right, let's go ahead and get started with the processor pipelining practice problems. So we're going to start off with a review. Go ahead, answer these two questions first on your own, then discuss them with your partner. All right, so why is pipelining a good idea and how does it do this good thing? Well, like everything else in computer systems, we're doing it for performance. We want to get performance. Pipelining is complicated. We wouldn't do this if it didn't give us performance. However, what pipelining does is it lets us run at a faster clock speed by chopping things up into smaller work. So if you go faster, but you do less work in each cycle, you don't actually get better performance. And this is really the key to pipelining. You get better performance from parallelism. It's not that you're doing each thing faster because each thing is now smaller when you're pipelining, but each of the part of the pipeline is doing something useful at the same time. So we have multiple instructions doing different parts at the same time. So we use the whole processor for a whole bunch of instructions at the same time. We do them in parallel. That's how we get performance. All right, now what is the key thing for making a pipeline effective and why is it so important? Well, keeping the pipeline full. If you have empty spots in your pipeline, that means we don't get any work done. One way to think about this is if you have an empty spot, if you have a bubble, when it gets to the end of the pipeline, there's no instruction there to finish. That means there's a cycle where the pipeline doesn't do anything useful. So bubbles are wasted cycles in the pipeline. And remember, the performance of the pipeline is from parallelism. So if we can't keep a lot of instructions going in parallel, we're not going to get our performance. All right, so here's the first question. Go ahead, read the question, answer the question on your own first, and then discuss it with your partner. All right, so if we take a look at this processor, we have a mix of instructions. This is how often they show up, and we have how long they take. And the idea is what's the fastest clock this processor can use? Well, what determines that? Well, it's the slowest logic path. Remember, we can't run the processor faster than the slowest instruction. So the answer is going to be 800 picoseconds, which is the slowest instruction here. All right, go ahead, pause the video, answer this new question on your own first, and then discuss it with your partner. Okay, so in this process, excuse me, in this question, we're going to look at how much of the time do we waste in this executing this program. And you can see how much of the instructions take a certain amount of time. Now, we can take a look at these and we can eliminate some of them pretty quickly. So we know that for these instructions here, since the processor has to run at 80 picosecond clock speed, we're not going to waste any time here. So 30% of the time we waste nothing. So that means we can't waste 80% of the time because we know 30% of the time we're not wasting anything. Similarly, if we look at this here, we know 20% of the time we're wasting 600 out of 800 picoseconds. So this is more than zero. So we know we're not wasting 0% of the time. Now the question is, which of these is it? Are we wasting 50% of our time or 20% of our time? And so to compute that, we can go and figure this out. So we take the total time, that's 30% of the time. We have 30% times 10 instructions. So for our 10 instructions, we take 800 picoseconds. The same thing for these ones here. So if you look at these ones, even though these instructions only need 200 picoseconds, we still use 800 picoseconds for them because that's how fast our processor uses. So if you add this up, you find that for 10 instructions, it takes 8,000 picoseconds. Not surprising since each one takes 800. Now, how much of that time is actually wasted? Well, for these ones up here, we waste no time because it uses the full 800 picoseconds. For these ones over here, we waste 600 picoseconds, and we do that for 20% of the instructions. And for these ones here, we waste 550 picoseconds. We do that for 50% of the instructions. So we can do the math, and we can see we waste 3,950 picoseconds. And then if you do the calculation, you find that's 49%. So the answer is about 50%. All right, let's go ahead and do the next question. So go ahead and pause the video, answer first on your own, then discuss with your partner. Okay, so the question here is in which stage is the branch instruction when its result is applied? So to take a look at this, you can look at this path here. So we see from this path is that when the branch instruction gets to memory, then it is sent back here and sent to be the next PC. So it's not used until we get to the memory stage. That's the answer. Now this is going to be really important in a later problem. So remember that when the branch instruction gets to memory, that's when we figure out what the next PC is to update. All right, so here we're going to practice some basic pipeline branching. So there are a bunch of questions here. So the first one is in which stage is the branch outcome applied? Give you a hint, we just talked about that. Then fill in the timeline here, showing what happens when the program is run here and the branch is taken. So we have A, B, branch equal G. So it's going to branch to G here. So fill in what happens here. Here you can see in cycles 0 through 7 and all your stages what happens. Figure out what happens with instructions C, D, and E, whether this is what we want and what you need to do and when to get the correct behavior. So go ahead, pause the video and answer this question together with your partner. All right, so let's go through this one. In which stage is the branch outcome applied? Well, as we saw before, it's in memory. When the instruction is over here in memory, then it goes around, and on the next cycle, we're going to update it. So let's fill in the timeline showing what happens when we execute this program. So in cycle 0, we do A, and A moves through our pipeline over the next 5 cycles. In cycle 1, we do B. Similarly, B moves through the pipeline, so it's going to execute 5 cycles later, right after A. Then we get branch equal. Branch equal goes through the pipeline, and it's going to execute here. Now what happens? Well, after branch equal, immediately after that, we don't know the outcome of the branch yet. So we still do PC plus 4, so we put in C. Then on the next cycle, we still don't know the outcome of the branch, so we put in D, and we've got C in the pipeline. On this cycle here, we still don't know the outcome of the branch. Remember, it's sitting here in memory, but we haven't yet taken that new PC and latched it in. So it's only at this point, when the branch is in the memory stage, that on the next cycle, we're going to correctly update and go to G. But look what's in the pipeline here. So in cycle 7, we're going to finish instruction C. So what happens with instructions C, D, and E? Well, they're executed. They go ahead through the pipeline and get executed. Is this what we want? No, it isn't what we want. Our code should have branched. After B, it should have gone to G, but instead we executed C, D, and E. So we should have skipped those. So what do we want to do to make this work? Well, if we detect that this branch happened, we need to go in and squash them. So we need to tell the pipeline that these instructions should not save their state. They should become no ops so that we don't execute them. All right. So let's take a look at that, and we're going to analyze how we can fix that. So go ahead, pause the video, answer the question first on your own, then discuss it with your partner. Okay, so the question here is, which of these programs will execute the correct code if branch is taken? And when you see the difference here, we have the same programs we had before, we've just inserted a bunch of no-ops. So we can take a look at it. Here's our A, B, and branch equal. And then the question is, how many no-ops do we need? Well, as we saw before, we need 3 no-ops, because when branch equals in the memory stage, the next cycle, instruction fetch, is going to fetch the right one. So if we have 3 no-ops in the middle here, then we will execute the correct branch. So the answer is the one with the 3 no-ops. Okay, so go ahead, pause the video, answer this question together with your partner. Okay, so let's take a look at this here. Can you change the code below to do something in place of the no-ops? So we had these 3 no-ops in here because we need to make sure that we didn't execute instructions we didn't want to. Can we do something more clever? And the hint here is to look for work that's done regardless of the branch. Because remember, these no-ops, these 3 instructions after the branch, are going to be executed no matter whether or not we take it or not. So if we can put stuff in here that's going to be executed anyways, we can save time. So let's take a look at our instructions. Can we move this instruction to after the branch? So can we put this one, excuse me, down below here and execute it? Well, if you look at what it's doing, this is actually creating the value in register 1, but we need the value in register 1 for the branch. So this has to come before the branch because we have to be able to compute it. So the branch depends on it, so we can't move this to after the branch. So that has to go before it. How about these next 2 instructions? Can we move these to after the branch? Well, the branch doesn't depend on them. These get executed every time we go around the loop. So if we move them down here and execute them after the branch while we're waiting for the branch to get all the way to memory, so it gets the memory stage, so it gets resolved, that's fine. So what we can do is we can switch this around. We can put the branch ones underneath here. Now, if you look what happened here, we've now filled up 2 of those no-ops with useful work. That means every time we go around this loop, we have 2 fewer no-ops, so we're going to get better performance. And the final question, can we move this add I to right after the branch? Can we put this in here instead of the last no-op? Well, the answer there is no. This is only executed when the branch is not taken. So if the branch goes up to loop here, we don't execute this, but this no-op is executed every time we go around the loop. So if we move the add I up there, it would be executed when it's not supposed to be. So we can't move that one. So here we're able to optimize things. We're able to move 2 instructions from within the loop into these branch no-op slots. And that means that as we execute this code, we only have 1 cycle in each branch where we're not doing anything, so the performance will be better. All right. Go ahead, pause the video, answer the question first on your own, and then discuss it with your partner. All right, so let's take a look at this question. We have a bunch of instructions that are in the pipeline. And the question is, which pipeline registers have reg write set to true? So remember, reg write is the thing which goes in here and controls whether we write back to the register file. So if you follow it through here, you can see reg write is stored right back in here and here and here, and it's set to say whether or not the instruction that's in that stage, when it gets to the end, is going to write into the register file. So let's take a look at what we've got. So first, where are the instructions in the pipeline? We've got these here. So in instruction fetch, we have branch equal. So does branch equal have register write set? Here's in the next stage, we've got the instruction dispatch. Oh, sorry, my mistake. In instruction dispatch, the next stage, we have add I. In execute, we have add. So these two instructions are now stored in these pipeline registers. And in memory, we have load word, which is stored in that register. And in the last stage, we have store word, which is stored in the write back. Okay, so is reg write true for these? Well, here's branch equal. So branch equal does not write to the register file. It doesn't store anything back. It's a branch. Plus, it hasn't been decoded yet. So we haven't even found out what the instruction is. So not only does this not write back, so it won't set reg write, but it hasn't been decoded yet, so we can't set reg write. So there's no pipeline register here because we haven't decoded it, so that's not true. How about for add I? Well, add I does write back because it's going to store its result in the register file, but it hasn't been decoded yet. In this pipeline stage, we just have the raw instruction. We haven't gone through the control logic to decode it yet. So here we are going to write back, but we don't even have a write back, a reg write register in this pipeline stage because we haven't done the decoding. How about add? Does add write back to the register file? Yes, it does, and it's been decoded. So this means that the write back bit here will be set true, so that when this instruction makes its way all the way to the end, it will set this write back and it will write to the register file. How about load word? Is reg write true for load word? Yes, it does. When you load something from data, you're going to write it into the register file, so this will have write back set. And finally, how about store word? Is reg write true for store word? Nope, it isn't, because store word does not write to the register file. Remember, it writes into the data memory. It has been decoded, but this is going to be a 0 or a false because this instruction doesn't write back to the register file. So that's the answer to this question. All right, now we're going to take a look at decoding the pipeline control signals. So go ahead, pause the video, try and answer the question together with your partner. If you get stuck here, you can do just the first one and we can go through that afterwards. Okay, so let's take a look at the first one here. So what are the control signals for add? So we want to figure out what's going on in the pipeline here. Well, so the instruction is type R. And so what's going to happen in the execute stage? Well, for it's an add, we want to take a value from the register file. So for add, we need 2 values from the register file. So this mux here is going to select read data to, or the register file. So it's going to be 0 to select the register file. What's the register destination mux going to be? Well, the register destination mux here is selecting where do I choose the register destination, from which part of the instruction is it coming. And if you look over here, you can see that this is for decoding instructions that are in I format or R format. So for the R format instruction, it's RD, that's the destination here. So we're going to want to take it from RD here. So this reg destination here is going to select RD, which are the later bits in here. So it's this one over here. All right, what else do we have? The ALU operation, well, it's an add, so it's going to do an add. And then what are we going to do with the results of this? Well, we're not branching. So branch is going to be false. So we're not branching. We're not writing to memory, not reading from memory. So both of those will be false. And are we going to write back? Well, yeah, we are going to write back. So an add instruction needs to write into the register file. So this register write is going to have to be true because we're going to write to it. And mem to register here is going to select the result from the ALU to send it to the register file. So it's not going to select the result from the memory. All right, let's go on to the next one. Sorry, here's the write back going through the pipeline in order to do the write. All right, load word. So this is an immediate type instruction. So what is the ALU going to take its data from? Well, the ALU is going to take its data, instead of 2 data from the register file, one of them is going to come from the immediate value. Remember, we're using this to calculate the address. And so we're going to do an addition with that. And we're going to send the address, sorry, getting a little ahead of myself. So the results of this are, okay, let's take a look at this. So we're going to take our immediate for the input to the ALU, and the other one's coming from the register. Where's the destination going to go? Well, the destination is 0, it's RT. So this is a load word. So now instead, since this is an I format, we have 2 registers here. So now we need to say that it's this register, not this one, which we're going to use to write back into the right register. So that's setting this mux here, the register destination, to say it's going to this destination, not that one as we saw before. The ALU operation is going to be an add because it's going to generate the address for the data memory. and we are going to read from the memory. So we set memory read to true. Sorry, because this is a load word. Sorry, this is memwrite. It should be memread here is set to true. And then the question is, where do we write it back? Well, now we're going to take the data from the memory instead of from the ALU, and we're going to use that data to write back into the register file. All right, branch equal. So how does this one work? Well, this is again an I-type instruction, but here for this I-type instruction, we're still actually going to use the two ALU sources because remember, we want to compare two values here, and we're going to subtract them because we want to create 0. Now, how about register destination? Well, we don't care what register destination here is because we're not going to write back. So we don't have register write. Register write is 0, so it doesn't matter which one of these we select because we're not going to enable writing back in here, so whatever's on the inputs, the register file doesn't matter. So we don't care about register destination. For the ALU, we're going to do subtraction. Branch is true, which is going to tell our branch comparator over here, should I pay attention to that? And for memory to register, do we take the results from the memory or from the register going back? We don't care which one of those we take because we're not going to write back, so it doesn't matter. So here we are, we send our output here, and this time our control is actually going to say, yes, we care about doing a branch, and we're going to use that to choose whether we do the branch. These are the two muxes where we don't care what the results are because we're not writing back into the register file, so it doesn't matter what data we send back to the register file. All right, let's take a look at a question about pipeline overheads. So go ahead, answer this question together with your partner. Okay, so what do we have here? We have a processor that takes 100 nanoseconds and 100 picojoules for each instruction. So that's how much it takes when it's not pipelined. It can be infinitely pipelined, great processor. And each pipeline register takes an additional 2 nanoseconds and 2 picojoules. So what that means is each time we add a pipeline stage, we're going to have a time overhead and an energy overhead. And so we want to know what the throughput, the time per instruction, the latency, the time to finish each instruction, and the energy for a 100-stage processor is. Okay, let's figure out what the original one is here. So for the original one, the latency is just 100 nanoseconds because it takes 100 nanoseconds. And the throughput is 1 instruction every 100 nanoseconds. The energy is 100 nanojoules per instruction. Okay, that's pretty straightforward. Now we pipeline it. So if we pipeline it, we have the 100 nanoseconds. That's the original time it took to do the instruction. Plus we have 2 nanoseconds of pipeline registers times 100 pipeline stages. So it's 300 nanoseconds per instruction. So that means each instruction takes 3 times as long to finish. But what's our throughput? So our throughput is 1 instruction every 100 plus 100 plus 2 nanoseconds. So this is the time it takes for each stage in the pipeline plus 2 nanoseconds. So it takes 1 nanosecond of logic and it takes 2 nanoseconds of pipeline register. So that means it will finish an instruction every 3 nanoseconds. Think about what the last pipeline stage in the processor is. It has 1 nanosecond of logic, took the 100 divided by 100, and 2 nanoseconds of pipeline stage. So every 3 nanoseconds we'll finish it. So it's 33.3 times faster, assuming we can keep the pipeline full. How about the energy? Well, we can do the same energy calculation, that we did for latency. And we see it's 300 picojoules per instruction. So it's 3 times as much energy. And then the question is this a good design? So what's the trade-off we made? We got 33 times the throughput for 3 times the energy. So is that a good trade-off? Well, it depends on where you are. If you look at this graph that we saw earlier, where we saw that we had a problem that our power went up and we couldn't increase it anymore, well, if we don't have any more power, 3 times higher energy doesn't really matter. We can't go there. So if we're really power limited, we can't afford 3 times energy, even if it gives us 33 times throughput. So as long as we're power limited, the answer is no, this is not a good trade-off. Okay, here are 2 extra problems. Go ahead, answer the question first on your own, then discuss them with your partner. All right, so the first question is speed up for a processor with 200 nanosecond frequency that's pipelined at 25 stages with latches that take 2 nanoseconds each. And this is similar to what we saw before. So the clock frequency is now going to be 25 times faster. So instead of taking 200 nanoseconds per clock, we'll divide it by 25, so we'll take 8. But we have 2 nanoseconds for the pipeline, for each of the pipeline registers. So that means it's 10 nanoseconds total per stage. So the frequency is now going to be 10 nanoseconds. It was 200 before, so we're 20 times faster. Oops, sorry. So what's needed to get better performance from pipeline processor? Well, higher clock speed. That's how we get, that's the benefit of making the instructions smaller by chopping them up. We have to execute multiple instructions in parallel. That's how we get actual performance because we're doing less each time. and keeping the pipeline full. If we don't keep the pipeline full, we can't take advantage of those. So we need all of these things in order to get good performance. All right, so go ahead with your reflection questions, pause the video, and answer them first on your own. Now that you've finished those, go ahead and swap your answers with your partner and help your partner out by describing what your partner found confusing and see if you can help your partner do a better, understand that in some useful way. And also write down what your partner helped you with your confusion. When you're done with that, that's it. Thank you.